We have seen how to provide reinforcement in the toe slab. So now let us find out how much the shear stress the toe slab experiences, and that is given by tau V. The formula is Fu upon BD, where Fu is the factored shear force. So the shear force is 150.535. That we'll multiply by 1.5 to make it a factored load, into 1000 to convert it into Newton, and divided by B is 1000 and D is 440. So we get tau V as 0.513 Newton per mm square. The amount of steel that is provided, or the percentage of steel, is calculated as 100 AS upon BD, and AS is 3141 mm square. So substituting this, we will get 0.714%. From table 19 of IS 456, we will get the permissible concrete, the permissible shear stress that the concrete can take, tau C, is 0.548. And since the permissible stress is more than what the toe slab is experiencing, the slab is safe in shear. So tau C has to be greater than tau V. Distribution reinforcement is 0.12%, and here we have taken the average of the depth at the critical section and at the towards the edge. So it is 460 plus 200 divided by 2 into 1000. So the distribution steel is 396 mm square. If we use 8 mm bars, the area of each 8 mm bar is 50.3 mm square. The spacing is 127 mm. Hence, provide 8 mm bars at 120 mm center to center. So this is the design of the toe slab. Next, we move on to the design of the heel slab, and there are 4 forces which are acting on the heel slab. One is the downward weight of the soil, which is 5.5 meter high. Then we have the load of the traffic, we have the self weight of the heel slab, and we have the upward soil pressure. Let us start by calculating the weight of the soil. We know that the width of the heel slab is 1.8 meters. We are calculating this for 1 meter length. Height is 5.5 and the density of the soil is 18 kilonewton per meter cube. So it is a simple rectangle. This is 1.8 meters. The height is 5.5. Okay, so the weight of this soil which is retained by the retaining wall, it is 178.2 kilonewton, and we need to find the centroid of this from the point C. So C is okay, this point here is C. So if we want to find out the centroid of this rectangle, it will be at half of 1.8, which is 0.9 meters from C. Next, we'll find out the live load. 18 kilonewton per meter square is the intensity of the traffic load for 1 meter length, and 1.8 is the width. So we get 32.4 kilonewton. Again, this is the width is 1.8, so half of 1.8 is 0.9 meters, and it lies 0.9 meters from C. Next is the self weight of the heel slab. So 0.5 is the thickness of the heel slab, 1.8 is its width, and 25 is the density of RCC. So this is 22.5 kilonewton acting at 0.9 meters from C. So these 3 forces that we have just calculated are all acting downwards. Next, upward soil pressure, soil reaction. So it is something like this. At below C it is 74.7, and at the extreme edge here it is 39. So we have taken the average of the two values, pressure intensities of 74.7 and 39, and multiplied it by the width of 1.8. And the upward soil reaction is 102.33 kilonewton. it's a trapezium, and we need to find out the CG of where this force is acting. Again, you can divide it into two parts, rectangle and triangle, a1x1 plus a2x2 divided by a1 plus a2, and that will yield an answer of 0.806 meters from C. The total shear force at C will be the addition of the weight of the soil, weight of live load, self weight of the heel slab, these are all acting downwards, and the upward is negative, which is 102.33. So the total shear force at C is 130.77 kilonewton. Now if we want to find out the bending moment, it will be these three forces multiplied by the lever arm of 0.9 minus, this is the pressure intensity acting upwards, into its lever arm of 0.806. So this gives us a bending moment of 127.312 kilonewton meter. You can do a check here to see whether the depth required is sufficient, the depth required is more than or less than what we have provided. Okay, but previously whatever we calculated, the moment values were higher than this 127, so this is not done again here. So keeping the depth same as that of the toe slab, that is effective depth of 440, total depth of 500, reduce the total depth to 200 at the edges. So the area of steel formula, we will put the value of mu here as 127.312, and we get the area of steel as 1280 mm square. Using 20 mm bars, we get the spacing of 245 mm center to center. Let us also check the shear stress, tau V. So 130.77 is the shear force unfactored. Let us multiply that by 1.5 to convert it into FU, and 1000 to convert kilonewton to Newton, divided by B into D. We get 0.446 Newton per mm square. So calculating the percentage of reinforcement required to get tau C as 0.45 Newton per mm square, area of steel is what is required as per the inverse calculations from table 19 is 0.44 BD upon 100. So initially what we got here as per the moment is 1280, okay, and what is required to make it safe in shear is actually 1936 mm square. So let us provide 20 mm bars at 162 mm. Let us round this figure and make it either 150 or 160 mm center to center. So this gives the actual AST as 1000 mm into the area of 120 mm bar divided by the spacing will give us 1962.5 mm square. So this is the area of steel which is provided. So had we gone as per this calculation of AST equals to 1280 mm square, we would get tau C is lesser than tau V. Okay, that means the capacity of concrete in shear would be less than what it is actually experiencing, and then eventually we would have to increase the amount of steel which is provided. Next, distribution steel, so that is 0.12% of the cross section, and 460 is at the inner face of the heel and 200 is towards its outer face. So the average of this is taken and we get 396 mm square. So using 8 mm bars, the spacing is worked out as 127. Let us reduce it to 120 mm. So 8 mm bars can be provided at 120 mm center to center. This is the detailing of the heel slab. So what happens here in the heel slab is the total downward force is more than that of the soil pressure from the bottom. So it is bending like this, which means this is the tension face and the lower side is the compression face. So the reinforcement has to be on the tension face. That is why in the heel slab the reinforcement is provided on the top, because the top of the heel slab is experiencing tension. And this is what we just calculated, 20 mm at 160 mm center to center, and the distribution reinforcement of 8 mm at 120 mm center to center.